Welcome to 163.01. Alright, so in this course we are going to be looking at classical analysis, or at least the beginning of it. So math is this funny thing in that when you start your undergraduate degree you tend to learn about calculus and linear algebra and other things like this, and we don't really teach you about the foundations of mathematics very much. That's because to actually get a good grip on it is quite a difficult and non-trivial task. And in fact, we're not even going to go right to the basics in this course either, because the further back you go, the bigger the wormhole becomes. And in fact, it led to one of the big crises in mathematics at the start of the 20th century, which culminated in Gödel's incompleteness theorem. But anyway, so what we're going to do in this course is we're going to examine essentially how the basic ideas of calculus work. So we're going to talk about things like limits and continuity, derivatives, and we'll start pretty much from first principles, but as I just alluded to, we can't start at the very beginning of mathematics. We're going to have to spend the first little while just setting up a sensible starting point that we can build upon. Okay, so once you've done this course, perhaps you may develop a bit of a taste for doing more of this kind of thing. But yeah, we'll see how we go. So today I just want to quickly talk about, to start with, at least the different types of numbers that we might be going to come across in this course. So we'll start as given the natural numbers. Okay, so some authors start them at 0, some start them at 1, it doesn't really matter. For our purposes in this course we're going to start natural numbers at 1, and we're going to assume that these are just given to us. Okay, we're not going to trouble ourselves about what having infinitely many things means or anything like that. We're going to assume that the natural numbers are all good. Now, one of the drawbacks of the natural numbers is that we cannot add and subtract them freely and stay within the natural numbers. Okay, if I try to take 3 away from 1, then I get -2, which is not a natural number. But obviously we've got this concept of -2, so that leads us to the integers, which we usually denote with a z. Okay, so these are the natural numbers over here. And these are the integers. Okay, and when we're working with integers, we can freely add and subtract them. And we have this thing here, the 0, which is known as an additive, or just an identity if you like. That's a special number that when we add in it to any other number, we get that number back again. It also means that every number has an inverse, which, for example, 2, the inverse of 2 is -2, if I'm talking about addition, and adding those together gives me the identity. Now, if you've done any algebra before, you'll recognize that property of having inverses and identities and being closed as forming a group. So the integers form what's called a group. But in the numbers that we're used to working with, not only do we add and subtract them, but we want to be able to multiply and divide as well. If we want to multiply and divide, then we have to talk about the rational numbers. Okay, so these are the set of numbers p and q, where p and q are integers, and where q is non-zero. These are called the rational numbers, as I just said. Okay, and so every rational number I can now multiply freely. If I multiply 2 rational numbers together, I get another one. I can divide by rational numbers so long as they're not 0, and that's fine. So if I've got p over q, I can take its reciprocal, q over p, so long as p is not 0, and that gives me a multiplicative inverse. I have a multiplicative identity, which is 1. And so basically put, the rational numbers have some extra properties, including this one here, where I've got a times b plus c, which defines how my multiplication and my addition work together. Gives me ab plus ac, known as a distributive rule. And I also have an ordering. Okay, so given r and s in our rational numbers, exactly one of r is less than s, r equals s, or r is greater than s is true. What that means is that I have this ordering which also is transitive, which means if I've got r is less than s and s is less than t, then that forces r to be less than t as well. So all this stuff is all kind of old hat to us. It's very familiar. It's how we've gotten used to working with numbers forever. But putting this all together, formally speaking, gives us a mathematical object called an ordered field. Okay, now the problem is with rational numbers being an ordered field, which we'll actually examine more closely a bit later, but I'll just mention it now quickly, is that there are gaps in it. Now you've probably met pi and square root of 2 and e before, for example. These are all examples of irrational numbers, numbers that can't be represented by fractions of integers. Now we can represent any of these numbers as close as we like using a rational number by, I guess, truncating its decimal expansion at a certain point. But these numbers do not actually exist in the rational number system, so that causes all sorts of problems when we want to start attacking it with calculus. So one of the first initial things that we're going to have to figure out in this course is how to go from the rational numbers to the real numbers, or at least to define some meaningful concept of the real numbers that we can work with. Because again, we're all familiar with the concept of a real number. It's kind of like a number you can measure with a ruler or something. But in terms of precisely defining the number system, it's a little bit trickier. Okay, so that's something we'll come back to. Alright, so we've got a little bit of preliminary stuff we want to talk about. Essentially just to fix some notation and some ideas. So I'm not going to get hung up on sets, and again, sets are their own own can of worms if you really want to look at the foundations of these. But sets are a collection of objects, or a set okay, and just going to write down a few various things that we'll deal with. So given a set, usually the objects are going to be numbers, sometimes they'll be sets, sometimes they'll be functions, but generally speaking we'll be talking about sets of numbers, e.g. numbers, functions, other sets. So given a set A, let's just do it pictorially. You may have met Venn diagrams before, so that will help. This is our set A. If I have an element x inside it, I write that x is an element of A using that notation here. If I have an element y that's not inside my set, then I write y is not an element of A. Okay, let's now have another set, make it a different color. And I'll call this set B. Okay, the intersection of the set, which is all the things here, is A intersection B, which equals the set of all elements x such that x is in A and x is in B. Okay, so just getting used to some notation here, that's called intersection. And so we talk about the intersection being its own set. Okay, the next one up is the union. The union is all the things that are in either. A union B is the set of all x such that x is in A or x is in B, or both. Okay, now whenever we use the word or mathematically, it's always inclusive. So X can be a member of A or B or both. That's how you are to understand the word or whenever we use it in a mathematical context. Okay, a couple more things. Let's just say that these are sets of real numbers, and here is my entire set of real numbers here. This thing out here, let's just take everything that's not an A, is called the complement of A. AC equals the set of all X such that X is not in A. Okay, now complement only makes sense if there's sort of some underlying set that we're taking subsets of. A few other things we like to talk about when we've got sets. A is contained within B, or A is a subset of B. What does that mean? Well, that means every element of A is also a member of B. We can also write this back to front, although it looks a little bit weird if you're not used to it. That means exactly the same thing. B is contained by A. To assert that two sets are equal, often a way of establishing this is to show that A is contained within B and B is contained within A. Alright, and last but not least, a couple of handy laws, and I'll let you see if you can figure out diagrammatically how these work. The intersection of A and B complement, okay, so we're looking at everything in our picture outside of the little blue region, is equal to the complement of A unioned with the complement of B. Okay, so maybe you can see that by looking at the picture. The complement of A unioned with the complement of B gives me everything not in the intersection. And similarly, we have a similar rule for unions. If I take the union, the complement, then I get the intersection of A complement and B complement. And these are known as De Morgan's laws.